Welcome back to the deep dive. Today we are taking, I think, a really fascinating turn. We're looking at the nuts and bolts of how software projects actually get built.
Hmm.
Specifically, we're diving into Haskell, the package manager stack, and this surprisingly manual process you have to go through to add a new external library.
Yeah, this is really a deep dive into the philosophy of tooling. Our source material today comes from these very precise, very practical notes of a programmer.
Right.
He calls himself an old software plumber, which I love, and he shares the detailed steps you need to take when, the standard automated conveniences just aren't there for you.
That contrast is immediately compelling to me. I mean, most package managers you see, like in Python or Node.js, they try to field you from the config files.
Oh,
You
completely.
get one command pip install or npm install, and it just handles everything silently in the background.
Right.
So our mission today is to understand the practical steps and I guess the underlying constraints of Haskell's stack environment when you have to do that work yourself.
And that really is the core difference we're exploring. Stack is, it's fundamentally built around reproducibility. It manages dependencies and builds your projects using these defined sets called snapshots.
Snapshots.
Yeah, and these are just huge collections of packages, thousands of them, that are all known to compile and work together.
Hmm.
The whole idea is to lock in your environment to prevent things from breaking later.
Okay, let's unpack this constraint right away then. Because for someone who is used to that modern automation, this is the first big aha moment.
Mm-hmm.
Stack doesn't have a simple command to just install a dependency.
It explicitly doesn't.
Yeah,
You would absolutely expect a command like stack add package or something similar.
right.
But the source material confirms it.
Yeah.
That feature does not currently exist. And this missing piece of automation is really the philosophical anchor for the whole manual process we're about to walk through.
That immediately makes me wonder, though, if I'm building a commercial project and I have to manually edit config files every single time I want to pull in a simple utility, isn't that just unnecessary friction?
It definitely seems like friction. But the Haskell ecosystem, it often values explicit control over, hidden automation.
I see.
Because Stack isn't going to update the configuration for you, you are forced to interact directly with the project's definition. It kind of reinforces this principle of immutability and precise control.
Huh.
You have to declare your intent to the system, not just ask for a result.
So if the command line is out, then the keyboard has to go into the configuration files.
Exactly.
Which means we have to know exactly which files control what. Where does this manual editing actually happen?
Well, you're dealing with two primary configuration files, and understanding their roles is really key. First, there's package.yaml.
Package.yaml.
Yep, this is where you, the developer, define all the specifics of your current project, your libraries, your executables, and crucially, your immediate dependencies.
Okay, so that's file number one. What's the second?
That would be stack.yaml. Now, this file governs the entire project environment. It specifies which snapshot you're using.
Ah.
You only need to edit stack.yaml if the library you want is so new or so obscure that it doesn't even exist in your current snapshot.
That's a really crucial distinction. So package.yaml is for working within the safe, pre-approved boundaries of the snapshot.
Precisely.
It's like saying, I need library X, and I know it's on my approved list, but editing stack.yaml is like crossing that boundary, and that sounds like a much bigger deal.
It is a much bigger undertaking. And for the purpose of adding a standard, well-established dependency, like the one in our source material, we focus entirely on package.yaml. We're staying in the safe zone.
Okay, so let's move into the actual implementation then. We've opened package.yaml. What is the specific anatomy of this file that the plumber guides us to?
So you're looking for the section that describes the core components of your project. If you're building a reusable library, you look inside the library block. If you're building a program to run, a standalone thing, you look inside the executables block. Within whichever one you choose, you have to find the dependencies list.
And this isn't just a matter of pasting text anywhere. I mean, YAML is white space sensitive, so the indentation really matters here.
Oh, absolutely.
We're structurally declaring that the project's main library component is now relying on this new package.
That is exactly right. And the specific library that the source material uses is optparse-applicative.
Optparse-applicative.
It's a wonderful example because it's a very common, very functional tool in Haskell for parsing command line arguments. If you're writing any program that takes input from the terminal, you'll probably need this.
So we need to explicitly tell our project, hey, we are now relying on this ability to parse command line options. The source material even gives the exact syntax and location, right? down to the line numbers.
He does, lines 36 and 37, which just perfectly captures the meticulous nature of these notes.
So what does that change actually look like?
It's surprisingly simple, assuming you are in the correct place, which, again, is the dependency section under the main library block.
And it looks like this.
Yum! Optparse-applicative?
That's it. You're just declaring a list item with a leading hyphen and a space, strictly following the YAML format. It's elegant, but, that elegance doesn't excuse the manual work required to get there.
It definitely forces a level of attention that automation hides. I can see why the developer calls this plumbing. You are literally turning a valve in the system.
A good way to put it.
But once we save that configuration file, we haven't actually accomplished anything yet in terms of running code.
That's the next phase. You've declared your intent in the blueprint, the package.yaml, but the system hasn't acted on it. The code for optparse-applicative hasn't been fetched or compiled or linked into your project.
This is where it gets really interesting. We move from text editing back to the command line, but now with a specific purpose. What's that first essential command?
It's the command that does all the heavy lifting, stack build.
Stack build.
This command forces Stack to read that updated configuration, identify the new dependency, download the specific version that the snapshot requires, compile it, and integrate it. Without stack build, the YAML edit is, well, it's effectively useless.
And stack build can take a minute, right? Especially if it's fetching a big package for the first time, you have to wait for that success message.
You do.
And once that dependency is compiled and linked, the simplest verification is just trying to run the whole thing.
Yes. The source material instructs us to follow up with dist-stack run. If your project executes without any errors about missing functions, maybe your program now calls something from optparse-applicative. That's strong evidence of success.
But our old software plumber doesn't just rely on intuition. A true engineer verifies the state of the system definitively. How do they show us explicitly that this library is now a permanent part of the build?
They use a fantastic combination of two commands to inspect the environment itself. First is low-test dependencies.
Okay, low-test dependencies?
Which just lists every single package currently included in the build environment.
And that output could be huge, listing everything from base libraries to obscure utilities, so they pair it with a filter.
Exactly. They pipe that whole list through grep to isolate only the package they just added. So the full command is stacksel's dependencies, grep optparse-applicative. This is the confirmation, definitive proof.
Well, let's talk about the specific output, because it's the most concrete piece of data we have from the source. What did that command return?
It returned optparse-applicative 0.18.1.0.
Ah, that detail. The version number 0.18.1.0 is so satisfying. It doesn't just say the library is present. It confirms which specific version from the snapshot is now incorporated.
Right. It ties the whole manual edit back to Stack's core promise of reproducibility.
It seals the deal.
It really does. If that library hadn't been successfully added, grep would just return nothing. That specific version number confirms you are working in a consistent, reproducible environment. The manual configuration was just the necessary permission step to activate it.
This entire sequence, the constraint, the manual config, the build, and the explicit verification, it really shows a developer who is deeply committed to understanding the underlying mechanism. It just contrasts so starkly with the fire and forget mentality of highly automated systems.
That is the key takeaway here. The absence of that automation forces this mechanical knowledge. You can't really be a great programmer in this environment without understanding the role of package.yaml and the implications of the snapshot system. It's control through diligence.
I want to connect this back to the source's title, Journal of an Old Software Plumber, Night-Long Tinkering with Floxes. This level of detail, this step-by-step documentation, it suggests a culture where deep mechanical understanding is really valued.
It does. It suggests the developer isn't just using Stack, they are mastering Stack. They're documenting the threads of the piping system.
Right.
So that when something inevitably leaks or breaks, they know exactly which file or which build step caused the issue. It's like preventative maintenance through explicit knowledge.
So what does this all mean for the bigger picture of software development, for project architecture?
I think it connects directly to this idea of dependencies as a cost. In an environment like Node.js or Python, the cost of adding a dependency is, it's essentially zero. One command line, maybe a few seconds.
Yeah.
It encourages this rapid adoption of lots of small packages for tiny tasks.
But the Stack workflow, as we've outlined it here, demands a higher initial investment. It's manual editing, saving, then a dedicated build step, then verification.
Exactly. And then we connect this back to the bigger picture, to the architectural choices you make, that manual friction point.
Hmm.
It actually becomes a factor in your decision making.
Hmm.
If you have to manually edit a YAML file and run a potentially time-consuming build process every single time you need an external package, that friction acts as a minor deterrent.
So does that higher cost maybe influence a developer to be more judicious, to maybe, I don't know, write a small utility function themselves rather than pull in a whole new dependency that has to be manually configured and maintained?
Yeah. Well, it raises a really important question for you to mull over, to explore on your own. Does a tool philosophy that prioritizes explicit manual configuration inherently encourage smaller, more tightly controlled dependency graphs?
Where developers just rely on fewer external libraries overall.
Exactly, favoring the language's own standard utilities instead.
Yeah.
It's a fascinating look at how tooling really shapes culture.
That is a wonderful thought to end on, the hidden architectural cost embedded in the simple act of adding one dependency. Thank you for walking us through the precise mechanics of Stack and the philosophy of the old software plumber.
My pleasure. It was fun.
We'll catch you next time on The Deep Dive.